Right. Good morning, everyone. So today is our last day for my square root shirt to celebrate. Before we get started, remember that exam 3 is due today and this afternoon. The final exam is going to be posted, and that's due on Monday. Also, for everything else, check that big announcement that I made, laying out everything that we need to know for the rest of the semester. But what I want to do today is our last topic. We're going to be hitting on a really important idea in talking about power series. It's called Taylor and Maclaurin series, but what it really means is we've been talking a bunch about how do you find series that represent functions. And the way we've been doing it is really starting with some, like the geometric series, we know that that works. And we've been starting there and substituting into it and differentiating and integrating those things. But what we'd like to see is a more systematic way. So if I just give you some function, how can you find a series for it? And if there's a way where we can actually figure out what the coefficients are. So if you have f of x and you know that it's represented by some series, there are some functions that aren't represented by series. In particular, every series is differentiable. And so if you're not differentiable, you can't be represented by a series. The ones we're looking at will be, but in general, things can be more complicated. But suppose that we know our function can be represented by a series on some interval with radius r. What are these coefficients? So for a power series centered at A, this is what it looks like, this infinite polynomial where in general we have x minus a's raised to these powers, not just x's. And we can actually figure out what these constants look like based on the function. So if we take this, and so we're thinking about working with this infinite polynomial, that's our series. If you put in a, then we get f of a, but on this right side, if you put in a, all of these terms with powers of x minus a, those become 0. So the first coefficient, the constant term, is the function value at a. So that's 1. Infinitely many to go. But how we can find the next one is if we take our series and differentiate it. And we know what happens is if you differentiate the function, then you can represent that by differentiating the series term by term. So applying the power rule to all of these terms, C0 is a constant, so it goes away. C1 x minus a, because that's linear, we just get the coefficient C1. Here, the power rule says bring the 2 down, so we get 2 C2 x minus a, and the new exponent is 1. In this n equals 3 term, the 3 comes down, we increase the exponent to 2, we get 3c3x minus 1 squared. And now, if we put a into this, every term that still has an x minus a is canceled, and we just get c1. So the coefficient c1 here is the derivative of the function at a. And we can keep repeating this process, differentiating and then substituting in the center point a. At each stage of the derivatives we take, we're going to be getting different constants, which means when we substitute in a, we're getting different expressions. So if we take the second derivative, this c1 goes away. In the second term, we're left with just 2c2. Here, the 2 comes down. The new exponent is 1. The term that we didn't write was 4c4 x minus a cubed. Applying the power rule to that, the 3 comes down. The new exponent is 2. Same move, if we put in x equals a, every term is gone except for 2 times c2. And you can repeat this again. If we take the derivative again, now this gives us 2 times 3 times c3. Here the 2 comes down and the new exponent is 1. The same deal in the term we didn't write. And if we put in a, the terms with x minus a are all gone, and we get 2 times 3 times c3. So if you keep going, what you see is that this is what always happens. The nth derivative at a is n factorial times cn. So the third derivative is 3 factorial times c3. The second derivative is 2 factorial times c2. And if you look ahead, you're seeing 3 times 4 times 5. The next derivative is going to bring a 2 down. And so we see that these factorials keep showing up. Repeatedly using the power rule, you are bringing more and more numbers down out of the exponent. And when you multiply those all together, you get a factorial. And so dividing both sides of this by n factorial, we see we actually get an explicit formula for what the coefficients look like. So that means if you know your function is represented by a series, this is what the coefficients have to look like. And so this is what we call the Taylor series. So for a function f, the Taylor series for that function centered at a is the power series, where the coefficients are these expressions that we found. The nth derivative of your function at the center point a divided by n factorial. And what we really demonstrated when we were working through what these c's are is that if your function can be given by a power series at all, it is given by its Taylor series. So the function is equal to this power series on the interval of convergence for this series. So we can write down this series, but it doesn't always converge. So you'd have to check independently once you figure out what this series looks like, whether it converges or not. As a special case, which is just a little simpler looking, and often examples look like this just because things are simplified a little bit. If you have a Taylor series centered at 0, that is called a Maclaurin series. But what it looks like is this Taylor series formula, but these a's here are just turned into zeros. So you're taking the nth derivative at 0 times x to the n rather than x minus a to the n. So the point of these formulas is that you can kind of by hand from scratch figure out a series for a function, not going through this substituting sort of ad hoc method that we were doing before. If you figure out what these coefficients are, you can start writing down the series. And this is especially helpful when we want to look at a function which has no similarity to 1 over 1 minus x or any of its derivatives. So as an example, let's find the Maclaurin series for e to the x and figure out its interval of convergence. So this means e to the x is our function, and we want to find these coefficients and write down the series with these coefficients times x to the n. So what we need to know is, what are all the derivatives of e to the x? Well, that's a really easy question. All the derivatives of e to the x are e to the x again. So every derivative you take is e to the x. And since every derivative is e to the x, every derivative evaluated at 0 is e to the 0, which is 1. So what this means is that e to the x is represented by its Maclaurin series, and this is just the formula for that. But if we look at this, these nth derivatives evaluated at 0, those are all 1. So what we still have is this factorial in the bottom. All these derivatives are 1, but there's still the factorial, so that means that the series for e to the x is x to the n over n factorial. And you can check using the ratio test, and I think we did this as an example, but it's a pretty straightforward ratio test problem, that the interval of convergence of this series is all real numbers, negative infinity to infinity. And so here, we found a new series. E to the x is represented by this series, and how we found it is using this Taylor series formula. Questions about getting this series? Okay. So one thing which is also important to point out is we've been finding series by other methods. If you use this Taylor series or Maclaurin series formula, you will get to the same place. Just the other methods are a little faster. And faster might seem surprising, but the reason why this was so easy is because it's really easy to tell what all the derivatives of e to the x are. If the derivatives keep changing, it can be more difficult. And your only hope for coming up with a series is that you notice a pattern in the derivatives and the derivatives evaluated at the center. If you don't really see a pattern, there's not much of a chance of writing down kind of a formula for the series. So for example, let's look at this function 1 over 1 minus x and find its Maclaurin series using the formula. So in this case, what we see, and I'll just kind of go down the columns here, if you keep taking the derivative, we get different functions every time. So 1 over 1 minus x, taking these derivatives, I kind of skipped over the quotient rule or the actual differentiating, but these are the derivatives. So 1 over 1 minus x, 1 over 1 minus x squared, 2 over 1 minus x cubed, 6 over 1 minus x to the 4th. And the reason why is, real quickly here, if you rewrite, say, this expression as 2, 1 minus x raised to the negative 3, the chain rule says bring down the negative 3, new exponent is negative 4, but you have a negative from the chain rule, the derivative of the inside, and so you have the 2 here, a positive 3, and then the new exponent in the bottom is 4. So that's where all of these are coming from. then what we want to do is figure out what are the terms of this series. These are all the derivatives. The corresponding terms are n equals 0. That's the 0th derivative, which is just the function evaluated at the center. 0 factorial is 1. That's just kind of a definition, times x to the 0. So you're dividing by 1, x to the 0 is 1. You're evaluating the function at 0. And so here you're actually going and saying, what do we get if we put 0 in? And we get 1. So we can compute that the first term of the series is 1. For the n equals 1 term, we want the first derivative at 0 divided by 1 factorial times x to the 1. So f prime of 0 divided by 1 times x. Now we again have to actually look at the derivative. And if we put in 0, we get 1 again. So the n equals 1 term is x. For n equals 2, we have the second derivative at 0 divided by 2 factorial times x squared. 2 factorial is 2. Evaluating this function, f double prime of 0, the bottom is 1, the top is 2, so we get 2 over 2 times x squared. The 2's cancel, we get x squared. The same deal if we pick n equals 3, we want f triple prime at 0 divided by 3 factorial, which is 6. But if you put 0 into this function, the bottom is 1, the top is 6, the 6's cancel, and you get x cubed. And this happens in general. The pattern continues where the top keeps becoming n factorial. The bottom is 1 minus x to the n plus 1. And so if you evaluate this at 0, the bottom is always 1, the top is n factorial, the n factorials cancel, and so you're just left with x to the n. So what we can see is that if we use this formula, we get the series x to the n. And we were starting to see that show up if we looked at these specific terms. We had 1, x squared. Okay, sorry about that. Let me pick up where I think I was. Right, so we're looking at these terms that we were giving, 1x, x squared, x cubed. We were getting this series 0 to infinity x to the n. But what is important to know is we already knew that. 1 over 1 minus x, we had said this is the sum of a geometric series. And so we know that this function is represented by this series. But the point is that this Maclaurin series formula, if you know the series already, this will give you that series. But if you don't know the series, this is a way of constructing it. So these two different methods, kind of Maclaurin series, Taylor series formula, and the sort of substituting, integrating, differentiating methods that we've seen, they get you to the same place, just by different methods. And in this case, why this works is because we're able to figure out a pattern in what the derivatives look like. If the derivatives kind of kept changing and we couldn't see how the derivative depends on which stage we're at, we wouldn't really be able to come up with a formula. So what's also important to point out is that if you change the center, things do change. You don't just put x minus a in instead of x. The coefficients do really change because you're evaluating them at the center, a, rather than the center 0 for the Maclaurin series. So e to the x, all of its derivatives are e to the x. Evaluated at 0, they're always 1. So the Maclaurin series for e to the x is x to the n over n factorial. If we try to find a Taylor series centered at 2, we go through the same process, but we're working at this different point 2 here. So the nth derivatives are all e to the x again, but now we're evaluating them at 2 rather than 0. And at least we know all the derivatives are e to the x. So all the derivatives evaluated at 2 are e squared. So this means that e to the x can also be represented by the nth derivative at, so this is the form of its Taylor series at centered at 2. These nth derivatives at 2 are always e squared, so that's where this one comes from. And we have x minus 2 to the n because we're centered at 2. So if you write this out, there is an extra e squared everywhere. And there's also, we have x minus 2's rather than x's raised to these powers. And if you check, this one we'll actually look at using the ratio test. The absolute value of an plus 1 over an. If we put an n plus 1 into here, we get x minus 2, an absolute value now to the n plus 1 over n plus 1 factorial. Dividing by an means take the normal terms and flip and multiply. And now we get the kind of usual cancellation. E squareds cancel, factorials cancel to leave you just the extra n plus 1 on the bottom. And x minus 2's cancel, giving you just one factor x minus 2 on the top. And the limit of this as n goes to infinity is always 0, no matter which x you pick. So this series also has an infinite radius of convergence. What is worth seeing is how these things are different and kind of why you would want to center it somewhere else. So as an example, let's look at e to the x. If we look at the terms of its Maclaurin series, so if we center it at 0, so e to the x is the blue line here. The purple line is the parabola using the terms up to x squared. And what we're looking for is that close to 0, this parabola is really close to e to the x. If we add another one, this cubic is even closer to e to the x around 0. If we add a fourth term and get a quartic, it is even better, especially around x equals 0. So if you take these partial sums, which are called the Taylor polynomials, they really well approximate your function close to the center. And these are the Taylor polynomials for the series centered at 0. So they're really good close to 0. If we zoom up a little bit, yeah, close to 0, they're really, really close together. And it gets worse as you go apart. But what we can kind of see is the cube term is good close to 0, but then it peels away. The x to the fourth term is good a little bit longer. And it's the red line is closer on this side too. So no polynomial is perfect, but adding more terms makes you good for a little bit longer. And if you were able to use infinitely many terms, you would be perfect everywhere instead of pretty good for some region. But if we look at the series centered at 2, these are the Taylor polynomials for that. And if we graph these ones, I mean, at 0, they're just not even close. But at 2, this parabola is really pretty good. And if we give ourselves the x cubed term, which is this next one, it's really good close to 2, and for a little bit longer, it's good for a little bit more of the graph than the parabola was. And if we make the quartic, so this has the x4th term in there, it is good for even longer than the red cubic was. And it's good, or really good around 2, and it gets worse as you go further away. So the point of this center stuff is the center is where your approximation by the polynomials is the best. So if you were to actually want to represent something by a series, what you would do, or kind of how you would pick the center, would be pick the point that you care the most about, because at that point you will get the best approximation if you only use part of the series. So this single function has 2 different series representations, and they both work on the entire line, but the benefit of having these 2 different ones is if you approximate with part of the series, that's a good approximation at different points of the function. Once we have this series, say e to the x is the series x to the n over n factorial, we can do the same sorts of things that we did with the previous series. We can say, well, what's a series for e to the x squared? One thing here is this talks about a Maclaurin series. This just means, so this doesn't mean use the formula. What it means is find a series centered at 0. And the sort of substituting in method ends up giving us a series centered at 0. So Taylor and Maclaurin series don't necessarily mean use the formula, but if you don't have a good method of finding the series, you can resort to the formula. In this case, we don't have to, though, because we can say e to the x. We know a series for that. We know a series centered at 0 for that. E to the x is the series x to the n over n factorial. That's its Maclaurin series. It's Taylor series centered at 0. So if we have e to the x squared, take the series for e to the x and substitute x squared in. Multiplying the exponents together, we get that the series x to the 2n over n factorial, that represents e to the x squared. And you can again check that this has an infinite radius of convergence. Actually, we knew that because substituting in doesn't change the rate, it's not going to change you from having an infinite radius. Substituting in can change finite radii, especially if you substitute in something like 2x, that can shift your radius, but since it's infinite, substituting it in is going to keep it infinite. And we can ask the same kind of questions involving calculus operations. What's a Maclaurin series for the integral of e to the x squared? Well, this means find a series centered at 0. And we know a series for e to the x squared. That's exactly what we found here. So we can find a series for this integral by integrating this series. So we want this function, e to the x squared. So here we know this is true, which allows us to say we want to integrate this series. How we do that is by integrating the terms of the series. And if we integrate x to the 2n over n factorial, this is a power rule problem. The n parts don't do anything, or at least the n factorial on the bottom doesn't. We apply the power rule to x to the 2n. So we increase that exponent by 1 and divide by that new exponent. And there's a plus c now. So this, and we can write out some of the terms, looks like whatever constant we pick plus x, that's if n equals 0, x cubed over 3 if n equals 1, 2n plus 1 is 3, so that's 3 there, 1 factorial is 1. And then we can keep going with the powers and this factor in the denominator matching, but then also these factorials. And in this case, part of the reason why I picked this example is this integral. So forgetting about the series stuff for a bit, this integral right here, this is not an integral that can be found explicitly. So you cannot write down a nice antiderivative for this. And it's not just that we don't have the techniques, it's that it's proved that you cannot write this down as a combination of like polynomials or trig functions or exponentials or logs or things like that. There is not a nice antiderivative. So kind of the best you can do is hope for some other way of expressing it. And what this means, or what we've done here, is say, maybe you can't write down exactly what this is, but here's a series for it. If you pick a big enough chunk of it, you can approximate this really well, especially close to 0. So you can say, take these first terms here, maybe forget the constant, leave it, or pick it with constant 0 or something. Here's a polynomial which really closely approximates the antiderivative that you're talking about here. So being able to express functions as series lets us answer a lot of questions that you just can't without it. You cannot write down an antiderivative for this in the way that we had been thinking of them by writing like an explicit function. But you can do it if you allow yourself to write it down as a series. As some other functions, notable functions that we can find series for, we can find a series for sine x. So first we want to think about what its derivatives look like. And its derivatives go in this sine-cosine cycle. So its first derivative is cosine, then negative sine, then negative cosine, then back to sine, and then you cycle through this. If you evaluate these at 0, we get all of the sines are 0, and cosine is 1, negative cosine is a negative 1. So these values of the derivative, 0, 1, 0, negative 1, 0, 1, 0, negative 1, that keeps repeating. So if we want to write this as a series, well, we know we have this formula for its Maclaurin series, which means, actually written out, that's f of 0 times the first derivative at 0 over 1 factorial times x. The second derivative is 0 over 2 factorial times x squared, and so on. What we can see is that all of the even powers, so 0, 2, x to the 4th, since the derivative is 0 there, all of those coefficients are 0. So what we get is that's 0. This term with x is just x. The x squared term is 0. This x cubed, well, the third derivative, that's negative 1. So that's minus x cubed over 3 factorial. And so the pattern we get doesn't have any even powers in it at all. It's alternating with odd powers over the corresponding factorial. So writing this out, we have a series. It's alternating, starting with +1 and then -1 and alternating from there. But we want to make sure that we only have odd powers. So we can write this and say every odd numbers are 2 times something plus 1. And so that's the exponents we have, and those are the factorials that we get on the bottom. So sine of x has this function as its Maclaurin series. And you can check using the ratio test, and most of these are using the ratio test because of the factorial, that this series also has an infinite radius of convergence. And what makes a connection is sine of x is an odd function, odd in the sense of its symmetry. And it's no accident that sine of x, an odd function, only has odd powers in its Taylor series. You can do the same kind of work for cosine, meaning it has the same cycle of cosines, or a similar cycle of derivatives, a similar cycle of derivatives evaluated at 0. But what you can also do, if you don't want to go through all that, is cosine is the derivative of sine. And since we know a series for sine, let's just differentiate that series. If we differentiate the terms of this series, which is how we actually find the derivative, the power rule, well, because the first thing is -1 to the n and 2n plus 1 factorial. Those don't have any x's, so those are just there. You apply the power rule to x to the 2n plus 1, which means the 2n plus 1 comes down. We decrease the exponent to 2n, and then doing a little canceling, the biggest term of the factorial is 2n plus 1, which cancels with what we have up here. And that leaves just 2n factorial in the bottom. So this is kind of similar looking. It's alternating, but it only uses the even powers, which again kind of makes sense. Cosine is an even function, so it only has even powers in its Taylor series. So before we see any more, I want to point out that on the final exam, there is going to be a formula sheet. This is the practice exam, which was posted if you were wanted to look at some problems. This has trig identities, a bunch of integrals, but kind of notably now, it has some power series given with the radius and intervals of convergence. So it has 2 we'd seen before, but also e to the x, sine of x, and cosine of x. And it has the Taylor series formula. These series, the reason why I'm pointing out that they're on this sheet is you do not have to justify where they come from. So at this point, we've introduced them. We've kind of seen why those series are the correct series. But at this point, you can at any point reference these series and just use them. You don't have to justify where they come from. So if you were given, say, this problem here, you could, without comment, just say e to the x has whatever series, and I substitute x squared into that. You don't have to justify where the series for e to the x or sine or cosine or 1 over x or arctangent come from. You can just use that these series as like black boxes, and then go from there. And you can just use their intervals of convergence, intervals and radii of convergence. So we can ask the same kind of questions, the integral of sine of x squared. We know sine has its series. If we substitute x squared into that, we substitute x squared into the series, which multiplies the exponent by 2, and we can integrate that series. If we integrate this using the power rule, the exponent increases from 4n plus 2 to 4n plus 3, and we divide by the new exponent. And if your interval of convergence's rate is infinite, then after integrating or differentiating, you'll stay infinite. The radius never changes when you are integrating. And the only thing is endpoints, which isn't really a concern in this case. And this is another example of an integral that we don't have, or there aren't techniques to find it, or find an explicit normal looking formula. So finding a series for it is kind of the best thing that we can do. What we can do with this is say, if we think about the definite integral, so the integral from 0 to 1 of sine of x squared dx, we can represent this as a series, and we can try to approximate it. So this kind of question, we can't just use the fundamental theorem of calculus, find, or in the way that we've been using it, by find an antiderivative, evaluate at 1 to 0, and get the number. But what we can do is say, well, this expression here, we know an antiderivative for it. That's this series. So evaluate this series from 1 to 0. Which, if you write it out, if you put in 0, everything is 0. But if you put in 1, all of the powers are 1, but you still have everything in the denominator. So this definite integral we can represent as a series. And when you can represent something as a series, an approximation is just stop adding things up after some point, and that's a guess. So this definite integral, this function which you could graph and see the area beneath it, from 0 to 1, that area is represented as a series. And so if we look at the first 3 terms, that's an approximation. And what's even better is this series that we write down is alternating. And alternating series, we can actually come up with bounds for how big the error is. So if we have this alternating series and we approximate it by 3 terms, the error is bounded by the 4th term, the 4th non-alternating part. If we look at the pattern here, this number keeps increasing by 4. So from 11, we get to 15. The factorials increase by 2. So 5 factorial becomes 7 factorial. If you multiply that together, that's over 75,000 in the denominator, which as a decimal is 0.000013. So in this case, this definite integral that we can't find exactly, we can approximate to within tenths, hundredths, thousandths, 10,000ths, like 1/100,000th, where this is within 13 millionths, which is really good. Another application, quickly, is this series 2 to the n over n factorial, show it converges and find its sum. So show it converges is easy, or I mean, you have to do it, but it's a kind of standard ratio test problem. So you know it converges, but finding the sum, that's a very different question. But what you can do is say, this 2 to the n over n factorial looks like I took this series for e to the x and put 2 into it. So e to the x is x to the n over n factorial. If you put in a 2, that's where this series comes from. And so what you know is that if I put 2 into this series, since that equals e to the x, I could just put 2 into e to the x. So this series, we know it converges by the ratio test, but in fact, we can say it converges to e squared because this is an instance of the Taylor series of e to the x. Another example using a series for inverse tangent. With not that much time, a surprising fact is if you take a polynomial and you find its Maclaurin series, its Taylor series centered at 0, you get the original series back. You get the original polynomial back. So this kind of matches with a polynomial is like a power series where most of the terms are 0, where all but finitely many terms are 0. So if you apply the formula to a polynomial, you're going to get that polynomial back. And as the last thing, which we kind of saw when we were talking about approximating that integral, is that we can have what's called the nth degree or nth Taylor polynomial. This is stop the Taylor series at the nth term. So it's the same formula, but you actually stop doing it at n. So here, you don't need to try to come up with a general formula. You can actually compute what each of these coefficients is. So for e to the x, if we think about what the terms of this series look like, the first Taylor polynomial is 1 plus x, so it stops at x to the first. The second polynomial uses the formula but stops at x squared. The third polynomial uses the formula but stops at x cubed. And what we won't talk about is that there's an inequality for how good these polynomials approximate your function. So we won't worry about that, but a problem we could look at would be, say, here's a function, find its Taylor polynomials at a certain point. And so that means find the first 3 derivatives, evaluate those derivatives at the center point, and then use the Taylor series formula. And given one of these polynomials, you can actually approximate values pretty closely. So sine of 46 degrees, converting that into radians is 0.803. If you stick that into here, you will get a very close estimate. So in some of the problems that that you can expect will be looking like find some Taylor polynomial for a function. This means use the Taylor series formula up to that point. So there's a lot more in here. Most of it, well, some of it is more examples of finding Taylor series. So those could be beneficial to look at if you want some extra series. The error stuff, disregard that. We're not going to talk about that. So the takeaway from this, I would say, is understanding the formula in order to come up with Taylor series, or often the beginning of a Taylor series, which is a Taylor polynomial. Okay. And with that, that's the end of the course. So these Taylor series are ways of representing functions as series, which is a very useful thing to have, especially because it gives you a lot more flexibility in finding some way to approximate a function if you can find an explicit form for it. So what to look out for, again, check out the big announcement, but the third exam is due by midnight tonight. This afternoon, the final is going to be posted, and that's due on Monday. I have my normal office hours today, but if you have any questions, let me know. And since I'm not having classes, I will mostly just be at my computer trying to be attentive to helping you guys out as you need it. So good luck with the end of our class and the rest of your classes, and stay safe.